In this lecture, we will discuss the technology of semiconductor gated conodots and how that system meet the technical requirements, the criteria put forth by De Vincenzo. Okay. So, the main idea or the seed of the idea was put forth by Loos and De Vincenzo in late 90s, where they proposed the electron spin in semiconductor quantum dots. The spin or the spin states of electrons can be used to store and manipulate information. The confinement that the electron experience in a gated structure can be represented roughly as a parabolic potential well. And in the absence of any magnetic field, these electron states are represented by a single energy level, which are degenerate, which has degenerate spin states. When you apply a field, this will split into spin up and spin down states. That whether the up state has a higher energy or the down state has a higher energy, that depends upon the G factor, the sign of the G factor. Okay. So, you can assign one of this as 0 state, another one as the 1 state. You can use this state to store and manipulate the information, and the transition between these two states can be driven by applying a electromagnetic radiation of appropriate frequency, which is equal to the energy difference. So, that is the qubit, and that is how you manipulate the qubit. This proposal is generally referred as LD qubit or Loos-De Vincenzo qubit. And there is a second proposal that is called ST qubit or singular triplet qubit. In the LD proposal, the spin state of single dot is used as the qubit state, whereas the ST qubit or singular triplet qubit is a double dot state, and there are two spin states. There are two spins in adjacent quantum dot which are linked by tunnel coupling. They can form, for example, these two electron system, this two electron system. This is a one electron system, whereas this is a two electron system. This can form either a single state or a triplet state. Of course, the triplet state has 3 states. We are referring to the T0 triplet state, up down plus down up. There is up and down states are there. That is not what we are referring to. We are referring to up down plus down up, and that is very close in energy to the single state. So, these two transition can be driven by a spin rotation, okay, or you can couple these two states by changing the exchange. So, in this LD qubit, you have spin up and spin down as your up and down states in the block sphere, but in the ST qubit, the singlet and triplet states are the qubit states. Now, in the light of the De Vincenzo criteria, these are very simple gated structures which actually can be lithographically defined on a large scale wafer, and each of this dot can be addressed by addressing or sending appropriate voltage signals to individual gates. And you can put an array of this quantum dot by putting an array of these gates on an appropriate wafer. An artistic illustration is given here. So, the scalability part is basically taken care when you have gated quantum dots, and individually addressable qubit, because if you want to initialize one of these, we will discuss how you initialize the states in one of the coming lectures, but you can do that by sending signals to the appropriate gates, individual gates defining the quantum dots. So, this is very attractive considering the scalability and the individually addressable qubit part of the Divincenzo criteria. And as I mentioned already, these are defined by micro and nanofabrication process, which is a standard fabrication process for the semiconductor industry. So, the overall realization scheme for the qubit is in accord with the current semiconductor processing technologies. Now, these devices are actually defined on two-dimensional electron systems. When we call or when we say a two-dimensional electron system, the obvious candidate which comes to our mind is the silicon-silicon dioxide interface, where you can get a thin accumulation layer at the interface by applying voltage on the gate. The gate voltage can induce band bending and actually can create a thin layer of electrons at the interface. And given, of course, depends upon thickness of this interfacial layer, and also the scattering mechanisms and how clean the interface, or given all those details, you can get a two-dimensional electron system. When I say two-dimensional electron system, and the z direction or normal to interface, there is only one k state available or one momentum state available. That means it cannot scatter in that direction. What that means, you have a sheet of electrons which is kind of pasted along the interface, and that is your two-dimensional electron system which you are getting if you have this configuration. And by appropriate gating, you can define electrostatically regions of low and high potential where you can have electrons trapped or tunnel barriers defined by gate voltages. There is a cleaner system, a cleaner two-dimensional system which are realized in semiconductor quantum well heterostructure, where you have a sandwich of material with different band gaps, such as gallium arsenide, aluminum gallium arsenide, or silicon, silicon germanium. Then you can get a thin layer of a very thin quantum well at the interface. This shows the conduction band profile of the structure as you go across. Of course, there is a doping layer somewhere here, but that again depends upon what kind of heterostructure you use. There are undoped heterostructures and there are doped structures. Undoped heterostructures work somewhat similar to this, but it has a cleaner interface. It's a gated, it's a enhancement mode device. It's accumulation mode device where you have a top gate to put carriers in the well, but in the doped structure you have dopants remotely sitting somewhere in the wider band gap, but these electrons will spill over into this quantum well, and you get the charge carriers, electrons there. Again, the interface in this system is much cleaner than here, so this tend to have higher mobility. And and it's very much easier to realize a cleaner system in this scheme. Here also, as I told, you have to put enough number of electrons in the system so that you have only one k state in the z direction or the direction normal to the interface below the Fermi level. Then only you call it a two-dimensional system. Okay, the same thing here. So when you do that, you get a thin sheet of electrons here, and that is your two-dimensional electron system, and that is your working platform, and that is your starting point. So now what you do is you are going to gate this structure. Either it could be dielectric gating, which is what generally done in MOSFETs, conventional MOSFETs. With the physics of that I am not going to explain much, but or actually you can do a Schottky barrier gating. The Schottky barrier gating is slightly different. Any metal semiconductor junctions can give a Schottky barrier. Of course, the barrier height depends upon the work function of the metal and the electron affinity of semiconductor. There will be a band bending, a thin repletion region in the defined semiconductor, and there is a barrier. In general, you can use these set of rules as thumb rules. So, an n-type semiconductor with a metal work function more than the semiconductor will be rectifying. That means you get a barrier. Similarly, for a p-type semiconductor, it is less than phi s, that means you get rectifying. So, these are the two situations what you need if you want to gate it. These are two situations you need if you want to inject electrons into it. So, the conditions are contrasting. If you want to inject electrons, you need a ohmic contact. If you want to gate, you need Schottky contact or rectifying contact. So, the depletion length into the semiconductor induced by the metal is given by this formula, where phi b is the barrier height and EVG is the voltage that you are going to apply onto the metal. Okay. And ND is your doping concentration, or other details. Okay. But the take home message here is you get a thin depletion region. Depletion region means it is depleted of any mobile charges. That means it is a dielectric medium which will act as a gate dielectric. So you don't need to put an extra dielectric like an oxide layer here. You can just use the depletion region or that thin region where the charge carriers are depleted as the insulator. So you are not going to put any foreign material on top of it. So you can get a better control and also better mobility. So what happens is, when you apply a voltage, so assume that you have a material like the shape of a slab here, and you put a piece of metal. Before that, the conduction band is here. The moment you put this metal and apply voltage, you are going to put the action of you putting the metal itself will deplete a little bit, but you can enhance that barrier even higher by applying this voltage. Okay. So when you put negative voltage, of course, barrier will be higher. Okay. So what that means is you increase the height of the barrier, because you are going to push this depletion region further and further into it. Okay. This what you are plotting here is the conduction band profile. So you are modulating the conduction band by the shape of the gate and also the voltage. Higher voltage or more negative voltage will give a sharper or taller barrier. So when you apply voltage onto this, you will get flat conduction band wherever there is no voltage. Then wherever this metal strip is there, then you will increase the barrier. So this barrier will act as a tunnel barrier between these two sides. So, or this will act as a dielectric medium for gating. So, this is the physics of Schottky barrier gating, and this plot here provides a rough idea of how the Schottky barrier height varies for gallium arsenide and for silicon with various material. So, here we are looking for something with a really high Schottky barrier. So, for gallium arsenide, I would say gold gives a very good Schottky barrier, n-type gallium arsenide, where for silicon the open circles here, actually gold is somewhere here, but platinum would give a better barrier for gold, for silicon. Okay. Now, but this is applied of course, this applies only to Schottky barrier gating. But if you are using a oxide gating, dielectric gating, oxide dielectric gating, then the dielectric material will be the barrier. So, you can use any of the other metals which is compatible with the processing. Okay. Now, that is the, in nutshell, that is the principle of Schottky barrier gating. Now, say you have defined now gates on surface of a two-dimensional electron system, and when you apply negative voltage onto this metal, you are going to deplete carriers under, but you will leave a thin region here. So, this thin region can act as a channel for electrons to go in or out, and by increase the voltage on these two gates, you can slowly increase the potential in the middle also. So, you can tune the barrier height and the barrier shape, or the confinement on the degree of confinement by voltages here. If you have this kind of geometry, say assume that this is the metal gate that you have deposited by a microfabrication process. When you apply voltages onto it, you will get electrons in the middle, electrons will confine to the middle and here, and wherever the gate is there, under those region you will not have any electrons. And this shape and the size of this confined region you can control by applying voltages. If you apply more negative voltage, the electron gas will be squeezed further. You get a higher degree of confinement. So, eventually what you will get when you go through this path, there is a small gap here, there is a small gap here, those are confined. So, this will provide channels, this will provide paths for the electrons to go into this region, come out. What you have here is a really small region which is defined by the voltage and also the lithographic parameters, that is the quantum dot. So, this is a small region, submicron usually in size, generally sub 100 nanometer, and the confinement usually in the shape of parabola, and you can get single particle levels. This is like quantum dot, but you are not using any nanoparticles or anything. It is a large wafer where you have isolate regions of electrons. So, you trapped electrons to small regions by gating technique, or this is like electrostatic confinement or electrostatic shaping. You can shape the conduction band profile electrostatically, whichever way you want. Okay. This is the principle of electrostatic gating. This is how all these dots which are used for this research is made. In this case, for example, I have a two-dimensional electron system, and this region will define source and drain, and these are the thin metal gates. When I apply voltage onto all of these, I will get a confined a quantum confinement of electrons into these two regions. When you apply voltage onto this, you get a kind of tunnel barrier here, tunnel barrier here, tunnel barrier here, because these two electrons are close by, and this will be a dip. These two will be the quantum wells. Of course, this is basically you need to think of like you have taken a sheet of electron and you have basically created regions of high and low or dips and troughs. That is your quantum dot, and these quantum dots eventually would form the qubits. Okay. This is the in a nutshell, this is the idea of electrostatic gating. Now, with this technique, you can define quantum dots of various shapes. This view graph provides kind of an evolution or a history of this kind of quantum dot. The first one came in very early, late 90s or early 2000. It's a pillar-shaped quantum dot where you have a two-dimensional electron gas defined by this stack sequence here, where the source is on top, source is on the bottom and the drain is on the top, and you have defined two tunnel barriers by the high band gap aluminum gallium arsenide layer, this yellow shaped region, and you have the quantum dot defined by this small disc shaped region in the middle, and the wrapping around these red regions, those are the gates which actually can change the electrostatic potential of the dot. This is a nice design, but it's not very easy to fabricate, but lot of interesting physics have been observed and discussed and probed using this design. These are vertical pillar shaped quantum dots because you actually take a two-dimensional electron system and etch like a pillar, and the path of electron flow is from top to bottom or bottom to top. These are vertical quantum dots. But the issue is these are not scalable, and how do you couple many quantum dots? Because eventually I want to couple various qubits, hundreds of thousands of qubits. I cannot do that. This is not a scalable design. Now comes the next generation of quantum dot, those are lateral gated quantum dots, where this is similar to what we just discussed, where you define the shape of the dot by appropriately shaped gates and apply voltage onto these gates, you get a confinement. So if you apply negative voltage on this one, all these things, you confine a small region here. It may not be circular, this is just a representation. And of course, this design has evolved over time, and lot of research has been happened using this design, generally called Siorga design, because he is the one who published this concept first. And this basically defines a double dot system where when you apply voltage on 1, 2, 3, this you confine a region, you get a quantum confinement in this region, and these set of gates you get in this region, and you can enable tunneling between these two or shut it down by appropriately choosing voltage between T, voltage on the gates T and M. So this is a double dot system. This also can be formed double dot. You just need to make sure that these voltages are increased. This is also increased. When I say increased, more negative. You can split this large pool of electron into two small pools and couple. Similar, that is what here also happening. If you don't use lot of voltage on these two gates, then this will be very large quantum dot. Once you increase the voltage on, once you make the voltage on T and M more negative, then you will split this electron this in two. Okay, that's what you are going to. Again, there is a limit, because this how scalable the system is. When you make hundreds of these dots on the wafer, it's very hard to couple each other, and a lot of fabrication issues are there. So, and also this is not how the industry works. Industry works on MOSFETs. So if you can get quantum confinement with the MOSFET geometry, that is the best part. Okay, and then come these quantum dots in silicon with the MOSFET geometry, silicon germanium system. So basically, what you have is a thin nanowire which is defined by gating or etching. Then you put another set of gate, which when you apply negative voltage, you will create a quantum well here in the middle. So you get tunnel barriers, and middle where is no gate, this is a well. So electrons are here, electrons are here, electrons are here. These two regions will have tunnel barrier, and this gate can be used to change the potential of this region. So this is the idea of MOSFET kind of quantum dot, but of course you need a really very clean system. This is idea is again very similar, but here you have a silicon germanium system similar to the gallium arsenide system which is used here, and you define this is an undoped system. So you have to define regions of transport or regions where you want electrons by putting an enhancing by putting a gate. So you have to basically put accumulation gates to increase the charge concentration, or to have charges there. So in this case, what you have is you have bunch of gates which are deposited on various layers of lithography. So the red ones here are gates which are used to accumulate charge carrier, whereas the green ones here are actually the one which defines a barrier. So this is source, this is drain, this is a barrier, then the red one comes here, that will give you a well here, this red one comes here, this will give a well here. So this is basically a double common dot, there are two wells here. Similarly, there is another path for electrons here. So this is a single common dot which actually can be used to sense the charges here. This charge sensing part we will discuss soon. Okay. So this is how the gate architecture has evolved over time for this technology. Now, scalability. So how do you make large arrays of these qubits? So you start from this concept, you have few quantum dots, 2 to 3 quantum dots. Then this has been now transformed to array of quantum dots by gating. You can see various gates are here, number of gates are here. When you apply voltage, you can have like 8 dots in this case and 2 dots on the other side. So this gate D will divide these two regions, that also defines the barrier, and these all will make sure that you get confined wells, an array of quantum wells, okay, array of dots. Same this concept, these are very similar, except that here you are using finger gates to define dot. Here each dots are defined by multiple gates. Here each dots are defined by one gate. For example, every red region will define the dot. Under that, and every green one define the barrier. That is what this is an array of 9 dots, okay, and this is an array of 8 dots, and you have 2 to 3 dots on the bottom to sense. Here are the 2 dots are there on top to sense. This is the latest proposal where you can have a 2-dimensional array of dots by having a crossbar network of various electrodes, and you can apply voltage on each, and you can get a 2-dimensional array of these dots. This is how the research or technology moving or taking forward as far as scaling these dots and making large array of larger processor. And this is a picture from the newsroom of Intel, where they have made a large 300 millimeter size wafer full of these kind of qubits. So what we are seeing now is a surge of work in this field happening over the last few years, and we have now reached a stage where we can get a large wafer full of these qubits. That big giants such as Intel now has already invested a lot of fund in this region, which actually says that the industry is also looking this research as a very serious research very seriously. Now, what we discussed so far is how these quantum dots are used to host a spin qubit. There are two kinds of spin qubit. One is the LD qubit, one is the ST qubit. In the LD qubit, single dot is 1 qubit. In the ST qubit, 2 dots form 1 qubit. There are advantages and disadvantages of both. Then these structures are realized on a 2-dimensional electron system, which are either silicon dioxide interface or silicon germanium interface, or aluminum gallium arsenide interface. Now these are formed by Schottky barrier gating or dielectric gating or oxide gating, and now various generations of these quantum dots we have discussed, and finally we have reached at the stage where we can have a wafer full of these qubits.